The topic of this video is bending stress on different kinds of cross sections. So previously we've been talking about twisting stress, but now instead of twisting profiles we are bending them. In this picture here you can see we have a beam which in unloaded condition is a straight one, but once we bend it, it takes a shape like shown in this picture. In this example, we are loading the beam with pure bending, so we have only external torque applied to the beam. When we bend a beam, like shown in the picture, what happens is that the bottom surface of the beam it gets extended, so it gets longer, and the top surface gets compressed, so it gets shorter. What this means is that the top surface that is compressed, it is under compressive stress. So the value for the stress is negative megapascals, and at the bottom where the material gets extended, the value for the stress is positive megapascals. A very important thing to notice in bending stress is that with the profiles, with any profile that is under pure bending, there is always a neutral axis. Along the neutral axis, highlighted in here with the dashed line, along the neutral axis, the length of the profile does not change. What does that mean? Well, when there is no change of the length, it means that the stress at neutral axis equals to 0. So there is no stress in neutral axis. Well, why is it important? We will learn that a bit later. So when we're talking about beams or beam-like structures, it's a very important thing to understand the coordinate system in the beams. So in beam structures, we always locate the origin of the profile to the neutral axis. When we have the origin at the neutral axis, the z-axis is pointing downwards, like shown in here. Y-axis points to the right, and the x-axis is located along the length of the profile, as seen in here. Previously, when we have been calculating the pure torque or pure twisting scenarios, we have been calculating load cases where the torque has been applied around the x-axis. But in the following scenarios, when we're talking about bending, the torque is no longer applied around the x-axis, but instead it is applied around the y-axis or around the z-axis. Now, when we want to calculate things where we are loading the beam around the y-axis or z-axis, we need to be able to calculate the second moment of inertia and section modulus for these scenarios. Quite often we are interested in calculating the stresses in such scenarios for those profiles, and for calculating the stresses we use these equations which we have been using before. The equation looks very much similar to the scenario to the previous equations. We have here the bending moment. This is the internal bending moment of the profile. Here we have the second moment of inertia for the cross section. Units are millimeter power to 4. And this here, the Z, is the distance from neutral axis in millimeters. Quite often what we want to calculate is the absolute maximum value for the bending stress, and in those scenarios or in those cases, instead of using second moment of inertia, we can use in the equation for stress, we can use the section modulus Wy. The section modulus can be calculated quite easily. How we calculate that one? Well, it is calculated like it has been calculated previously. We take the second moment of inertia and we divide it by the maximum distance from the neutral axis to the edge of the profile. In this scenario, in this example, the distance from the neutral axis to the top surface is bigger than the distance from the neutral axis to the bottom, and therefore the Z max value is the distance from here to top of the profile in here. So here we have a scenario where we have this same profile, and we are given the second moment of inertia for this profile in this task. The second moment of inertia for this profile is 215 10 to power 4 millimeters power to 4. We are asked to calculate the stresses for the distance of 36 millimeters from the neutral axis, so Z1 in here. We are asked to calculate also for the Z2 to the bottom of the profile and Z3 to the top of the profile. In this case, the equation which we're going to be needing is this one. So sigma equals to bending stress divided by second moment of inertia multiplied by the distance. How we calculate it in this case? Well, the sigma 1, stress 1, will be quite simply 6 times 10 to power 6 Newton millimeters. It is the bending moment. It was also given in this task. So the bending moment divided by second moment of inertia multiplied by 36 millimeters, which is the distance from here to here, and we get a value of 100 megapascals. We repeat the same process with other distances. The bending moment remains the same. Section modulus, second moment of inertia is the same. Only thing that changes is the distance. For sigma 2 we use the Z2 and we get 173 megapascals. And finally the sigma 3, and now it's important thing to notice that the sign for the Z value, instead of multiplying with positive 92 we multiplied by negative 92, and the reason is that the positive direction for the value Z is downwards from the neutral axis. And now, since we are going up from the neutral axis, we're going to negative Z direction. It means that we have to multiply the MB divided by IY with minus 92. And the stress is then negative 257 megapascals. So this means that the top surface is on compression and the bottom surface is on extension, tensile stress. Well, from the IY, if we wanted to get only the maximum value of the stress, we could have divided the IY with Z max, which is 92 millimeters. We would get the section modulus like so, and then we could have used this equation to calculate the maximum value for the stress. But it is worth noting that if we use this equation, we do not know the sign of the stress. So if, for example, in this example, we can see that instead of getting negative 257, we got only 257, and now we would have to know that the top surface of this profile is in compression. Well, this is how we calculate the stress. But one thing that we don't know yet is that how do we get these second moments of inertia for the profiles? Well, luckily, for basic shapes like rectangles, circles, hollow cross rectangles and hollow shafts, we have these basic equations for calculating the second moment of inertia in bending. For example, here For calculating the second moment of inertia for this profile around y-axis, the equation is b, which is the width, multiplied by height, which is the height here, power to 3 divided by 12. And this is a very basic equation, and we're gonna need this one a lot. It is worth noting that in this scenario, in this example here, in this equation, because we are calculating the second moment of inertia around the y-axis, this is the b and this is the h. If we would be interested in calculating this around the z-axis, then the b and h, this would be the h and this would be the b. Okay, well, from your formulas data sheet, you will find these basic equations. You will find them; they are listed in your formulas data sheet, so you don't have to learn these by heart. With this information, we can now start calculating some basic examples of bending stresses on basic profiles.